Alrighty folks, now let's go over the law of cosines, and at the end we'll talk a little bit about how we can use the law of cosines to modify the area of a triangle formula. So first things first, law of cosines is going to be used to solve triangles in the following situations. If we have two sides in the included angle, known as a side angle side situation, or if we have three sides that are known, a side 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 situation. There are essentially going to be two forms of the law of cosine equations, and while there are patterns associated with each of the forms, they are not something you need to memorize for my class. You will have them as equation sheets or notes to review back to during any sort of tests or exams you might have. The first form is what we use when we have a side angle side situation and need to solve for a missing side. The general pattern here is whatever side we're looking for, we're going to add up the squares of the other two sides and then incorporate the angle associated with the side that we want. That's going to be true for any of the sides we're going to go for. If we're solving for C, we're going to deal with cosine of C. If we're solving for A, we're going to deal with cosine of A. If we're solving for B, we're going to deal with cosine of B. The other set involves when we're working with side, side, side situations, and we're trying to solve for individual angles. The pattern here is essentially going to be for whatever angle we're trying to solve for, we're going to subtract the squared associated side, and then divide by the other non-associated sides. So whatever we're adding up here in the numerator, that's what we're going to divide by in the non-squared form. That's going to be true whether we're looking for the cosine of C, subtracting C squared, the cosine of A, subtracting A squared, or the cosine of B, subtracting B squared. So let's apply this to some examples. So this first one, we want to solve for a triangle that has a side of 3, a side of 7, and an angle of 130. This is going to be a side angle side situation. So the first thing I'm going to do is solve for my missing C side. Using the equation that C squared is equal to A squared plus B squared minus 2AB times the cosine of C. And my A, my B, my cosine of C, that's all given to me here in the prompt. So the only thing that's new is my C squared. So I'm going to go ahead and plug in what I know, such that my C squared is equal to 3 squared plus 7 squared minus 2 times 3 times 7 times the cosine of 130. I'm going to chuck all that into my calculator. I'm going to get a C value that's equal to 9.2. Now that I have a third side, I can now transition to my side, side, side equations to solve for one of my missing angles. I can solve for either my A or my B, but I'm going to go with my A for this one. So the cosine of A is equal to B squared plus C squared minus A squared over 2 times A times C. Plug in what I know. The cosine of A is equal to 7 squared plus 9.2 squared minus 3 squared all over 2 times 7 times 9.2. That's going to give me the cosine of A is equal to 0.97. If I apply an inverse cosine, then A is going to be equal to about 14.4 degrees. So now I have my C angle, I have my A angle, I only need my B angle now, so I can find my B angle by simply doing 180 minus my A angle of 14.4 minus my C angle of 130 to give me about 35.6 for my B angle. So all of my missing components solved using the law of cosines. Next problem. In this one we have another similar side angle side situation where we have side of A, side of 2, side of 3, and a angle measurement of 60 degrees. So first things first, I want to solve for my missing side. In this case, my missing side is B. So B squared is equal to A squared plus C squared minus 2AC times the cosine of B. Plug in what I know, and I get B squared is equal to 2 squared plus 3 squared minus 2 times 2 times 3 times the cosine of 60, which simplifies down to B is equal to the square root of 7. Now that I have my third side, I can transition to my side equations. And I can solve for either my A or my C. I'm going to solve for my A in these notes. Once I have my A value, I can then use my subtraction to find my C value. So the cosine of A is equal to B squared plus C squared minus A squared over 2 times B times C. Plug in what I know. Cosine of A is equal to square root of 7 squared plus 3 squared minus 2 squared all over 2 times the square root of 7 times 3, which means that the cosine of A is equal to about 0.76. Take the inverse cosine of both sides, and my angle A is going to be approximately 40.9 degrees. At this point, to find my angle C, C is equal to 180 minus angle A of 40.9 minus angle B of 60 to give me angle C at 79.1 degrees. All three components solved with our law of cosines. This third one's a little different. Here, we're given all three sides right off the bat. So we don't have to do our first set of equations. We can jump right into our solving for the angles. In fact, I can solve for any of the two angles using my law of cosines, and I'll use my subtraction to find my third angle. So, because I was favoring the A angles previously, this time I'm going to instead solve for my B and my C. I'll do B in purple, and I'll do C in orange. So, solving for B, the cosine of B is equal to A squared plus C squared minus B squared over 2 times A times C. Plug in what I know. The cosine of B is equal to 6 squared plus 12 squared minus 15 squared over 2 times 6 times 12, which simplifies down to the cosine of B is equal to negative 0.31. If I take the inverse cosine of that, angle B turns out to be 108.2 degrees. Angle C, well, the cosine of angle C is equal to A squared plus B squared minus C squared over 2 times A times B, such that the cosine of C is equal to 6 squared plus 15 squared minus 12 squared, all over 2 times 6 times 15, such that the cosine of C is equal to 0.65. Take the inverse cosine, and C is equal to 49.5 degrees. So I have my B angle, I have my C angle. To find my A angle, I'm going to take my 180, subtract from that the 108.2, and subtract the 49.5, and I'll get an angle A that's equal to about 22.3 degrees. Last example problem. Same sort of thing of a side setup. First step, pick which angles we're going to solve for. This time I'm going to solve for angle C and angle A. We'll do angle A in blue. So, angle C. The cosine of C is equal to A squared plus B squared minus C squared over 2 times A times B. Plug in what I know. The cosine of C is equal to 4 squared plus 3 squared minus 6 squared, all over 2 times 4 times 3. Toss it into my calculator. I get the cosine of C is equal to negative 0.46. Inverse cosine, C is equal to 117.3 degrees. Cosine of A is equal to B squared plus C squared minus A squared over 2 times B times C. Plug in what I know. My cosine of A is equal to 6 squared plus 3 squared minus 4 squared, all over 2 times 6 times 3, such that my cosine of A, toss it into the calculator, is equal to 0.81. Inverse cosine gives us an angle A measurement of 36.3 degrees. So to find my angle B, I'm going to take my 180, subtract from that my 117.3, as well as my 36.3. That gives me an angle B measurement equal to about 26.4 degrees. Those are my 4 examples for the law of cosine. The last thing I want to talk about is how we can use the law of cosine to actually manipulate the traditional triangle equation. Whenever you learn the triangle equation, you probably learned it as the area of a triangle is equal to 1/2 base times height. And that it usually required that you had the height given to you, or more usually you had a right triangle to work with. But sometimes you don't have triangles that have a well-defined height. In those cases, we can actually use the law of cosines and SOHCAHTOA to simplify our equation. So under SOHCAHTOA, we can identify the height of any triangle by drawing in an imaginary height into our triangle. Make it perpendicular, and we get ourselves a right triangle. In that right triangle, the sine of A is essentially going to be equal to the height of that triangle, of the bigger triangle, divided by the, divided by the C of the original triangle, which is the hypotenuse of the small triangle we made. Therefore, height is essentially equal to the hypotenuse times the sine of that angle, or side C times the sine of A. So I can take that h and plug it in to this h here. If I do that, it changes the area formula such that my area formula is now 1/2 of side B times side C times the sine of angle A, where B and C are the sides, A is the included angle of a law of cosine SAS situation. And you can use it for any triangle, even if you don't know the height. And that's really it. So if you have questions on things, please ask. Otherwise, we'll touch base later on.